to do a whole lot of homework. That is, I'm going to do it. Most of the time, I don't do that many homework, but this particular section is very interesting, so I'm going to do, well, almost all the homework that I assign. As always, if you know how to do the homework, there's no need to watch this video. This is just for in case you have any questions or see how I do it. The problems in here are not necessarily more difficult, but I do find it more interesting, which is why I choose to do most of it for you. Now, first, let's look at problem number 5 on page 350 on the homework. We're in section 4.1, I guess. Actually, no. Well, never mind what section it is. We are on page 350, number 5. Now, anytime you do word problems, you have to read the problem very carefully and gather all the information that is provided. You have a 10-foot ladder, okay, which is leaning against the wall. The top of the ladder is sliding down, and how fast is the bottom of the ladder flattening out, basically. Therefore, let's draw our wall. Okay, here's the ladder. To do this type of problem, the first thing you have to consider is I forgot to lock up my board. So anyway, getting back, the first thing we need to consider is what is the constant, what is changing. Now the 10-foot ladder, the ladder's length is not changing, so that is a constant, and the unit is the foot. What's changing is the top of the ladder is coming down this way, okay, at the rate of 2 feet per second. 2 feet per second. And then the question is, what's this thing doing? Okay, you know this thing is sliding out, but how fast? So this thing is going to whatever. And so let's make up some variables. This is 10 foot. So this one would be, we will call it x maybe. Okay, and what we're trying to figure out in this problem is what is dx by dt equals to what? And that is what we're shooting for. And so what is this height? This thing here is, let's see. I will look at my notes. Okay. In my notes, I will call it b equals to okay, this we'll call it b, and I should finish reading the problem. How fast is the bottom sliding out when the bottom equals to 5 feet per exactly when the bottom is 5 feet. Now notice b is changing, okay, and this height is changing, but that isn't. So that will be the foundation. I will call the bottom length as b. So you have what it is the relationship. We'll change the x to b. That way I'm consistent with my notes. Equals to what? When b has to be equal to 5. Alright? So how do you find the value of b? The b, we'll call this thing h. Okay? And the 2 feet per second, is that a second here? The 2 feet per second is just means that dh by dt equals to 2. In fact, it's negative 2 because it's reducing. Okay, the sign does matter. So having this kind of problem, the hard part is just to identify which one is what. What is the rate of which change is what? Okay, the next thing we have to figure out is the relationship of b and h, and that relationship is, we'll use the Pythagoras theorem. So then the relationship is called b equals to the square root of 10 squared minus h squared by the Pythagoras theorem. Okay, it's a squared plus b squared equals to c squared. And then we take the derivative with respect to t. So db by dt equals to 1/2. And the square root goes on the bottom. Write this down. And then take the derivative of the inside by the chain rule, which is minus 2h times dh by dt. That's a straightforward application of the chain rule, which this can be cleaned up to look like this is cleaned up somewhat. 10 squared minus h squared, and this is evaluated at dh by dt equals to minus 2. Okay, and h is evaluated at what was h again? 5. No, h is not 5. H is, do we need to calculate h? Yeah, well, we've got to calculate h. Can't get out of it. So h equals to, use the Pythagoras theorem again. H equals to, I'll write it down here, where in this formula we should calculate h equals to 10 squared minus 5 squared and the square root. And so once you plug all those numbers in, you get some kind of answer. So dh by dt, dB by dt, which is what we're looking for, is equal to, that's 75, square root of 75, divided by square root of 25, okay, and then times, that's negative, yeah, let's not forget the negative, and then times minus 2. So the whole value is going to be positive, and when the dust settles, you get 2 square root of 3. That's feet per second. And that is the right answer. All right. So that's a quick, easy problem for this type. And then we will come to the next problem. The next problem I will do is problem number 9, which says, okay, problem number 9, where is it? On the same page, that says 2 buses are driving along parallel freeways that are 5. What? Am I sure it's problem number 9? I guess so. All right, we will do it. Okay, 2 buses driving along parallel highways, and that are 5 miles apart, one heading east and the other heading west. Assume each bus drives at 55 miles an hour, so they both going the same speed. Find the rate where the distance between the buses changing when they are 13 miles apart, heading towards each other. Okay, now they're 13 miles apart. So we'll draw this thing. One bus goes this way at 55 mph. The other bus goes the opposite way, goes back also at 55, which is fine. Their distance is 13 miles apart. All right, and here's s equal to 13 is where we want to do the math. However, we need to figure out what is ds by dt when s equal to 13. That's what we're shooting for. All right, so again, this is a Pythagoras theorem problem, right? Because you have a right angle triangle here. And then we'll call the bottom here A. And then what is dA by dt? Now here's a small trick to this problem. How fast is A changing? dA by dt is equal to it's going this way 55, that way 55. It actually equals to 2 times 55. Okay, the unit is miles per hour, I believe. Yeah. So dA by dt is actually 110. That's miles per hour. Anyway, so that's the part that you have to catch. Once you've done that, then and the distance between the highway is 5 miles, right? Yeah. This distance, this 5 doesn't change. That's the constant. So that's changing, that's changing, that is not changing. So with that relationship, we can figure out, calculate something that we need to calculate, which is this thing. All right, so let's write down the Pythagoras theorem, which is S equals the square root of a squared plus 5 squared. Now, in this kind of relationship, anytime the variable is changing, you have to use the variable. But if it's not changing, you can use the constant. So we'll do ds by dt. ds by dt equals to 1/2 times square root of a squared plus 5 squared, and then 2a, and then dA by dt, where you have to calculate the value of a again. What is the value of a? The value of a equals to Pythagoras theorem, 13 squared minus 5 squared, which equals to 12. Okay, a equals 13 squared minus 5 squared, which is 12. Okay, and then dA by dt is 110. Is right here is 110. And then by the time, so then you substitute these values in here and come up with the answer, which I will not go through the details so as we can save time. And so that's the answer. If you need to look at it, you see it well. Yeah, it's pretty clear. So and that would be how you do this problem. So the distance, and then let's move on to the next problem, okay, so that we can get through it faster. Next, we have, let me clean off the board. Next, let's look at problem number 11. Problem 11 is actually based on problem 10, so we have to do problem 10 first. So it's like 2 problems for the worth of 1 or something. So you have a guy who's 6 foot tall walking away from a 10-foot tall lamp post at the rate of 3 feet per second. So here let's draw a diagram. Here's the lamp post. Okay, here's guy. The lamp post is 10 feet tall, and that doesn't change. Okay, the guy is 6 feet tall. That also doesn't change. Okay, here's your guy, here's the lamppost, and the guy is walking this way, walking away from the lamppost. And how fast is he walking? He's walking at 3 feet per second. Now, what does that mean? That means, let's call, okay, let's get the variables right. This is, this number here is, we'll call this distance here as a, okay, and then and the whole thing we'll call it h. That's a, and then a, so a and h are changing. All right. So what does the problem say? A is changing. How fast is a changing? A is how fast the guy is walking. So dA by dt as given is how fast is he walking? 3 feet? Yeah, 3 feet per second. So that's how fast the guy is changing. And then what we're trying to figure out is how fast is this thing right here is the shadow. Okay, what is the rate of tip that moving away from the pole? Okay, that is this point. This is the distance of h. Okay, the tip of the shadow from the pole. We're doing problem 10 for now. Okay, and then we'll do problem 11. So problem 10. So how far is the tip moving away from the lamppost? In other words, what we're looking for is what is dh by dt equals to what? Okay, that's the question. And this is the information we have, I believe. All right. So once we have all this stuff, now we know that means we need to find a relationship between h and a. How does h and a relate? Well, these two are similar triangles. This one right here, the small one, versus the big one. Those are the two similar triangles in this story. And their relationship, by the rules of similar triangles, is that this part compared to the whole thing, that is h minus a, this part, okay, compared to the whole distance, which is h, is the same as 6 over 10. That's their relationship. And then if you clear this out a little bit, that equals to so now we're gonna do some basic algebra, right? That is 3 over 5. So that equals to 3h equals to 5h minus 5a, and then so 5a put over here. That's a 2h. So h equals to 5a divided by 2. My division line is too long. And that should be it. Yep. And therefore, dh by dt, take derivative of both distances but with respect to t, which is 5 over 2 dA by dt. So that is what we're looking for. And this is given right here, which is 10 over 2. What? No, sorry. dA by dt is 3, so it's 15 over 2. That's feet per second, or 7.5. All right, now having done that, let's look at the next problem. The next problem asks, that is what we're trying to do, problem number 11, asks, what is the rate at which the tip of the shadow move away from the guy, okay, at this exact point where a equals to 10? Well, being that the shadow is moving away from the pole is that's at 7.5, and then the guy is moving in the same direction. So the answer is simply that. So the answer is the shadow is moving at -3. That is this value, because they're moving in the same direction. So the speed subtracts. So then this is 7.5. So the answer for the shadow moving away from the guy is 7.5 minus 3 equals to 4 feet per second. And that would be the answer. All right, that's the end of that problem. All right, let's move on to the next one. The next problem I want to talk about is problem number 23, which is quite straightforward. You have a triangle with two constant sides. So that's pretty good so far. You have a triangle, two constant sides. One side is 3 and the other side is 5. The sides don't change. So that's reassuring, right? And so what is changing? What's changing is the angle between the two sides. So we'll call it theta, because we always do. So theta is changing at a rate of 0.1 radian per second. So that's given. d theta by dt equals to 0.1. And find the rate at which the area is changing when the angle is pi over 6. So we need to find out dA by dt when the angle is equal to pi over 6, 30 degrees. All right. So And how would you do that? Well, all the information are pretty straightforward. We just need to know how does the area relate to the angle in this case. And to do that, you have to dig out the old trigonometry, where there's one rule that says, well, if you have two sides and an angle, the area is called, the formula says area equals to 1/2 AB cosine C, cosine theta, where AB are the sides and the theta is the angle between it. There's this is taught at some point in trigonometry, maybe. Yeah, probably. Anyway, if you don't remember, just look it up. Okay, it's a straightforward formula of how to calculate the area. So now that we have our formula, then we'll straightforward calculate the derivative. So dA by dt equals to, we're gonna do, well, A and B in this formula is constant, so we can just write down the numbers. So 1/2, 3 times 5, I'll write it down. Let's get rid of that. 1/2, 3 times 5, and then cosine of theta. And this is d theta by dt, where this is to be evaluated at d theta by dt is 0.1, okay? And then theta equals to pi over 6. So with that, you can calculate the numbers and straightforward get to the answer. Now here's my notes, and I will stop right here to so that we can get to the next point. And this answer is correct too. I checked. Next, a cylinder is leaking water. Isn't that awesome? Problem number 29. We have the cylinder is leaking water, but you don't know what rate is leaking, and that's what we're looking for. Okay? Now the cylinder, it has a height of 2 meters and a radius of 2 meters. So we have a cylinder, which is this thing. And the radius is 2. And then the rate which the water's, you need to find at the rate which the water is leaking out. What does that mean? That means you're looking for dV by dt, okay? Water leaks out by volume, right? So you're trying to figure out what is dV by dt equals, that's our purpose of life for the moment. So what is dV by dt? If the rate at the height, when the height is 1 meter, so the water is at 1 meter, 1 meter, all right? And when the water and the height, that's the h equals to 1. All right, at h equal to 1, it says the height is decreasing at 10 centimeters per minute. So dH by dt equals to 10 centimeters per minute. 10 centimeters is 0.1 meter. So we have to write down 0.1 because everything else is given in meters. You have to watch out for these traps. So suddenly they shift it to centimeter, and if you don't pay attention, then your answer will be way off by 100 times or something like that. So so it's 0.1 meter per minute, okay? M per m, let's just say. Okay, so now our units are taken care of, so let's do this problem. Having said that, we have h and r is 2. R is constant. The cylinder is not changing in size. So that much is steady. So we need to find a relationship between V and H, and that will be the volume of a cylinder. The volume of a cylinder is given as pi r squared, that's base area, okay, times the height. That's the normal, which is, in this case, being that r is a fixed number at 2, that is 4 pi times h. So that's a pretty quick calculation, right? So then dV by dt is then, of course, 4 pi dh by dt, where dh by dt is substituted at 0.1, h equals to 0.1, and then so that answer would be 4 pi times 0.1, which is 4 pi divided by 10, or 2 pi divided by 5. That is the right answer. Divide by 5, and what unit is it? It's meter cubed per minute. Now, I believe your book missed in the answer key missed the cube, but always remember, you're talking about volume. Volume is always cubed in units, and that's 29. See, as a piece of an easy problem, and yet it sounds impressive, because before before you learn derivatives, it's much harder to figure out who knows how fast this stupid thing is flowing, right? But now you can totally figure it out, and it doesn't even take a lot of work, which is what's so awesome about it. So next, I want to do problem number 35. Next, let's look at problem number 35. Write it down first. I've been forgetting to write down the problem number. Okay, problem number 35, where it says gravel is being unloaded. Yay, we're unloading gravel. How exciting. Gravel is being unloaded from some truck and falls into a pile shaped like a cone at the rate of 10 cubic feet per minute. All right, so what does that, what's the cubic feet? That's dV by dt. So first we're given that the volume is, the dV by dt, the change of volume is 10 cubic feet. See, feet cubic per minute. All right, and our gravel is being unloaded. So that's it's unloaded into the shape of a cone. Okay, there's my cone, and the radius of the cone base is 3 times the height. All right, so here's our height. What are we looking for? Rate the height. Okay, we're looking for the height. It says the radius is 3 times the height, so the radius will be 3 times the height, like that. Find the rate at which the height of the gravel changes when the pile has a height of 5 feet. So what we're looking for is dH by dt when h equals to something, 5 feet. Okay, so all the units are consistent. There's no trap here, and we will get this thing to come out. Now this is remember, this is a cone, not a triangle, right? But I'm not going to draw the cone out to reduce confusion. But the volume of a cone is taught at some point, and if you don't remember, you can look it up readily. But the volume of the cone is called V equals to pi r squared h divided by 3. Or in our case, is equal to, so V equals to, r is equal to 3h, so r squared is 9h squared. So that the whole thing equals to, I'll just write it down, 3h squared times h divided by 3, and that's yeah, and then so that equals to 3 pi h cubed. Correct? Yep. And then from this point on, you take the derivative. Okay, so then dV by dt equals to 9 pi h squared dH by dt. Now from this point, then you can substitute all the necessary values. This thing equals to 10. Okay, h is what was h again? H is 5. Yeah, it says right here. We need to figure out what h is, 5, and then calculate dH by dt, which is what we're looking for. This is what we're looking for. Okay, and that should come out very easily. And you can see my answer here if you're not sure. All right. And then with that, we'll go to the next page. And I checked the answer, it is correct. Next, let's look at problem number 37. You are on the ground, not moving, stationary. That means you're not moving, so that's good. And you're looking at some bird flying at the rate of 10 meters per second. the bird is 40 meters above your head. So this number is 40, and we presume that the bird is flying horizontally. Okay, so this distance is 40 meters above your head. How fast when the horizontal distance between you and the bird is 9 meters? So that's important. Okay, its horizontal distance is 9, but this distance is changing. All right, but anyway, so there's the bird. Here's you. Here's bird. How fast is the... So the bird is flying horizontally at the rate of 10 meters per second. Does the angle when the horizontal distance of you and the bird is 9 meters? I got to thinking. I'm not sure which way the bird is flying. I don't care. Let's assume the bird is flying away. Okay? And the bird is flying away at the rate of 10 meters per second. It probably doesn't make any difference. But we'll just, yeah, it might not matter which way the bird is flying. 10 meters per second is all that we care for the moment. How fast does the angle of elevation change when the distance is 9? Now, what is the angle of elevation? Okay, here's you, here's bird. The angle of elevation is, it might not even matter in this problem, but the angle of elevation is defined as this angle right here, theta, which is this angle here. But anyway, that is, that is the angle. This is level, okay? Whatever this angle makes with the horizontal line is called the angle of elevation, which would, by basic geometry, that means this angle here. How fast does the angle elevation change? So what we're looking for in this problem is d theta by dt equals to what? Okay, and then, so having said that, let's so let's do this. Now what do I have? Problem 37. Oh, okay. I was looking at problem 39. It's not making any sense. All right. 37 is a little bit better. And then, what? I didn't even write down. Okay, so to calculate that, then we will call something A. I call this one A because A is changing. That's how A is the distance where dA by dt is the 10 meter per second that the bird is flying. We'll write down that right here. dA by dt as given equals to 10 meter per second. All right. So how does A relate to theta? The next step, we need to come up with a relationship between A and theta. Now the A and theta is some kind of a cosine. Okay. No. We'll use tangent. Okay. So I haven't written it. I don't even have write it down. All right. So to find the relationship between A and theta, we use the tangent equation, which is opposite divided by adjacent is tangent theta. So let's write down this equation. 40 divided by A equals to tangent theta. That's the definition of the tangent. And then let's take the derivative of both sides, which is with respect to t. So then this one takes the derivative equals to minus 40, okay, divided by a squared, and then dA by dt equals derivative of tangent is secant squared theta d theta by dt. All right, so at this point, then we need to do all the grunt work. Okay, what is A? A equals to 9, where we substitute all the required numbers, and this is what we're looking for. This thing right here, right? So all the rest need to be just calculate it, actually. What is secant squared? to calculate the secant, which is 1 over cosine, you have to find out this length. And this length is equal to square root of 40 squared plus 9 squared. And then, so the secant squared is, secant is 1 over cosine. So secant squared equals to hypotenuse over adjacent squared. So that part is 40 plus 9 squared over 9 squared. That equals to secant squared. And then a equals to 9. Okay, a equals to 9. And then dA by dt equals to 10. So once you plug in all these numbers, then you get the right answer. Which, yeah, okay. So I'll let you look at my notes to see. Yeah, I made a small mistake. That's why so many scratches in there. Somehow I put this as minus instead of plus, so I end up getting the wrong answer at first. So let's hope you don't make the same mistake, and then everything should come out very nicely, which it did eventually for me, and I checked. So that's that. Let's now look at the next problem. Problem number 39. Now, sorry, I said something wrong earlier. I said dA by dt is 9. It is not 9, it's 10. This kind of mistakes is what one reason I don't like to do grunt work, because I have a tendency to make this type of mistakes. Anyway, yeah, put in the right number and then you get the right answer. Now let's look at problem number 39. 39, some lighthouse is on some island 4 miles away from the closest point, fine, on the beach. If the lighthouse rotates clockwise at a constant rate of 10 revolutions per minute, how fast is the beam of light moving across the beach 2 miles away from the closest point on the beach? All right, so let's draw our picture to see what this is talking about. Here's our lighthouse. And the theta, here's theta, and theta is changing at the rate of 10 revolutions per minute. So d theta by dt, one piece of information we're given, is 10 revolutions per minute. What's that? Each revolution is 2 pi, so 10 revolutions, 20 pi. 20 pi per minute. All right. Okay, so that thing is turning and turning, so the light shines clear across over here, and you see the light moving, across the beach. All right, and this distance is fixed. Okay, the lighthouse isn't moving; it's fixed at 4 miles, and then and this particular distance is 2. We'll call it A. Okay, I like to call these things A for some reason. A equals to 2 for the moment, but A is changing. In fact, what are we trying to look for? We are trying to look for dA by dt, right? Yeah, how fast is this light moving? In other words, we are looking for dA by dt. By the way, the theta is decreasing because it's turning this way. So we'll put a negative sign there, just for the heck of it, to show that the angle is decreasing at this point. So A is 2, and you know that A is also decreasing because the light is, swinging clockwise, which means it's going this way, like the clock. If you remember how a clock works. Nowadays, people don't even read the analog clock anymore, right? Because a digital clock is much, much better. And I don't keep an analog clock in the house myself. Anyway, so clockwise means turning this way. And so we are looking for dA by dt. We always figure out what are we doing, like what are we looking for? D, we know that's a D. dA by dt, where A equals to 2. All right, so far so good. We're in problem 39. So that's the problem. So now the next thing we need to figure out is what's the relationship between A and theta. And as before, in fact, just like the last problem, A and theta is, and there's a number here, so we'll use that number. That's the fixed number. That is A over A divided by 4 equals to what? Tangent theta. Again, that's by the definition of the tangent. So then, yeah, let's take the derivative. dA by dt. okay, times 1 over 4. That equals to secant squared. The derivative of tangent is secant squared. That you need to memorize, probably, especially for this part, because it seems like we do that all the time. d theta by dt. Okay, so as before, we need to figure out what secant squared is when a equals to 2 and this side equals to 4. So secant is hypotenuse over adjacent, is 1 over cosine. So then we'll figure out this side is by the Pythagoras theorem, 4 squared plus 2 squared. And so then you figure out secant squared just like previous one. dA by dt is here, and then you can calculate d theta by dt rather conveniently, as you can see here in my notes. I will not do the rest of it, but the answer ended up being 100 pi miles per minute. 100 pi miles per minute is very, very fast. That's like over 300 miles per minute, not per hour, per minute. So that's super fast. Okay, but that like just wishing through. All right, so let's look at the next problem. Now, so far, the problems we have done are pretty easy, right? I mean, in terms of straightforward, the formulas are not very complicated. But however, problem 43 is more involved than the rest. It involves a more complicated problem. More complicated formula. However, the principle is the same. You do the same thing you've always done. So let's look at problem number 43. 43 says, first let me find it. Okay, you have a diamond. You have what is that? A baseball diamond. A baseball diamond is actually just a square. At least that's what this thing says. Look at that. Okay. It's not a diamond. I mean, a square is a diamond, but you don't call it a diamond. A square is just a square. But anyway, we call it diamond, and which is fine. And then the diamond has a side length of 90 feet. Now, if you don't know much about baseball, wait a second. Let me read the problem first. Where's my problem? 43. Okay. A batter hits a ball towards second base at 80 feet per second. Yeah, okay. So then we're not going to draw a diamond. We're just going to draw a square. So here's your baseball diamond, okay, which we'll tilt it this way. Here's the guy. The guy is no, that's not the guy. That's where the guy comes from. Okay, the guy is hitting a ball this way. And then while he himself is running this way. Okay, so far so good. Now 43. This yeah, he's hitting a ball at 80 feet per second, and then he himself is running at 30 feet per second. At what rate does the distance between the ball and the batter change when the runner has covered 1/3 of the distance to the first base? 1/3 of the distance, really? The distance is 90. They couldn't just tell us 30. But anyway, so the question is, what happens when this distance is 30, and that one we don't even know what that is, right? It's somewhere less than, well, still inside the diamond, so to speak. All right, so we will draw this thing out on the side, the triangle that matters to me. So first, let's point out that the guy's running at 30 feet per second, and he's gone 1/3 of 90, so he is at 30. So there are two numbers that's repeating itself. That is, this angle here is 45 degrees, being that this is a diamond, or pi over 4. So here's theta. The angle here is fixed. Okay, because the ball and the guy are going relationship at a fixed angle for the moment. So that's 30, and what is this? What do I call it? A. All right. So the distance is 30, and is going at 30 feet per second. Similar here. This one's 80 feet per second, and it's gone 1 second. So this is 80 plus is at 80 feet per second, both. And then this is the distance what we're looking for. Okay, so what we're looking for is what is ds by dt, where here's the guy and there's the ball. And what is the distance between them? How is that changing? So ds by dt equals to what? But in the meantime, you got to understand that, okay, we'll call this distance b. And the angle is pi over 4. Okay, pi over 4. So we have a where db that by dt, that's the speed of the ball, that equals to 80 feet per second. Now dA by dt, which is the speed of the player, dt, is equal to 30 feet per second, while they have gone exactly 1 second. So the distance here is also 30 and 80. That makes it slightly, I guess, simpler or more confusing, depends on how you look at it. It doesn't matter. The point is that, so we have all this information, so we need some formula that connects b and the angle and a to give you s. Now what kind of formula gives that, where the third side is equal to something to do with the other two sides plus the angle between? There's a name for that, is as your book has told you, is go think about the law of cosines. What's the law of cosines? Is from trigonometry, but suffice it to say, the law of cosines says something like this. I will write down the law of cosines here, where it says c squared equals to a squared plus b squared minus 2ab cosine c, cosine theta, where theta is the angle between the two sides. So you have a and b, like two sides, and then the angle in between. Then the third side, we'll call it c. Actually, we'll call it s in our case. That is the law of cosine. Okay, the law of cosines simply states this stuff, which is fine. So now we have this formula is much more involved than what we had previously so far, but that's not all. The formula also has two variables on the side, okay? And then furthermore, you have a product, so you have to apply the product rule. So this thing is going to be long, but no harder than what we've done before. So if it has two variables, we will take care of two variables. We are given the two values, so we'll just plug it all in and then hope that we don't screw up. So having said that, let's do this. Okay, so then let's take the derivative of this thing, bearing in mind implicit differentiation and, more importantly, product rule right here. So let's do that. And what does that give us? That equals to all right, that equals to, now I will do it the way I did it, because, and I don't think it's much harder than how the book did it, but yeah, but that's how I did it, so I will write it down this way. You can also do it without taking the square root, just do implicit differentiation of both sides, which will be fine too. Minus 2ab cosine theta. And I'm going to take the derivative of this thing, which is equal to ds by dt equals to 1/2. Okay, and then the square root of all the stuff on the bottom, a and b and stuff, right? And then I will write that down later. And then up here we have 2a dA by dt plus 2b dB by dt ignore that, minus the cosine theta. The theta is not changing, okay? That's cosine of pi over 4. So we'll write it down. The cosine pi over 4 is the same as the 2. It's a constant because our angle isn't changing in this story. So we'll write down 2 cosine pi over 4, which is some value. And then AB is works like this. Remember, so do the product rule, which is A times dB by dt, first term times derivative of the second, plus the second term, B times dA by dt times derivative of the first. And takes the square root of all this stuff, and which I will write it down again. B squared minus 2AB cosine theta. Alright, so now we have all this stuff, and that might look, I don't know, confusing or something, but it's not. Well, okay, it might look confusing, but all the numbers are here. Why? Because we know what A is, okay? So A equals to, and that's just S. And cosine theta, as we have stated earlier, theta equals to pi over 4. Cosine theta is not a variable here. So that's pi over 4. And in this big thing, there is now we're just a matter of substituting numbers. That is, A equals to 30, okay? Where A equals to 30, B equals to 80, and then dA by dt equals to right here 30. That's also dA by dt is also 30. And 30, and then dB by dt equals to 80, as we have had earlier. So and then this is just cosine 4. In other words, all variables in here are accounted for. You just need to plug it all in and crank out the numbers like I did, and then you will come up with some kind of answer. Now I will show you what I wrote. See, and what's good is I didn't even mess up. See, after plugging all that stuff in and working things out a little bit, you get the answer of 62.5 feet per second, and that's the answer after you patiently plug it all in. And as you can see in my solution, it's not necessary to use the calculator right away, because as it comes out, if you let me pull back a little bit. Okay, as you can see, if you just work on it a little bit, the things sort of cancel out fairly nicely, so you have a fairly short answer in the end before you have to use the calculator, so you don't have to punch in that many numbers. But if you do punch in all the numbers, make sure that you get it right, that you have enough parentheses to take care of everything, that this whole thing is the numerator and that's the denominator, and where you're taking the square root. Everything needs to be done systematically and neatly and not messed up. Okay, if you forget to put in, say, a parentheses on top, you're not gonna be coming out with the right answer. So then it would be such a shame to go through all this and then the calculator gave you the wrong answer. But the calculator is never wrong, okay? If you come up with an answer that isn't right, there's only one explanation. You punched in the wrong thing somehow, and you violated your calculator rules. So it's very important if you don't get the right answer, that you figure out what you're doing wrong with the calculator. That marks the end of this section.